All right, so in this antibiotic resistance simulation, I have set aside my bacteria, my low resistant red ones, my moderate or medium resistance blue ones, and my high resistance to antibiotic yellow one. I roll the die. So it's a 5, and looks like my antibiotic was taken at the right time. So what I'm going to do is I'm going to kill off 5 of the weakest bacteria first. So I can take away 5 of these. Notice I didn't take away from the moderate or the high resistance, only take from the lowest resistance ones. If there were 4 left, let's say I rolled and there were only 4 left, I got rid of all my low resistance and there were no more reds, then I would take away from my moderate resistance ones, okay? And then in terms of reproduction, for the next round, I put 1 of each category that's left. So since there was 1 yellow, I put a yellow. Since there are some blues, I put a blue. And since there are some red, I add a red. Notice I didn't double it. I just added 1 for each type of bacteria left. Let's say I got rid of all my reds and I was starting to reproduce. I would only obviously add to those that still exist.
Now, there are some calculations of percent error that you have to make to figure out how much your population has changed. So I'm going to walk through the process with some made-up data to help you do the calculations. In the beginning of the simulation, let's say you have this breakdown of bacteria, of low, medium resistance bacteria. And then at the end, let's say this is the population. Now we can see the population has clearly changed, but the question is, how much has it changed? How much has the high, medium, and low resistance bacteria changed? Well, we can use a sort of modified version of percent error. So we can take our ending numbers, our observed numbers, we can input them into our percent error chart. And then we might be tempted to just put in our starting population numbers. So for high resistance, put in 2, then 6, and 17. However, when we look at the total population numbers, we started with 25, but then we get down to 11. So there's no way we can expect to have 17, 6, and 2 because we only have 11 to end the simulation. However, if we're trying to figure out if evolution has happened, we can figure out what were the beginning percentages of the low, medium, and high resistance in the original population, and if no evolution occurred, then we expect to have the same percentage breakdown of low, medium, high. For example, if the medium resistance was half of the population or 50% of the population in the beginning, then it should be 50% of the population at the end, which would be 50% of 11 would be 5.5. So how do we do the math? Well, the first thing we're going to do is find out the initial percentages of each type of bacteria. To do that, we take our 17 divided by our 25, and we get 0.68, which is the same as 68%. Then we take our 6 divided by our 25, we get 0.24, which is 24%. Then we divide our 2 by 25, that's 0.08 or 8%. Now, actually using the decimals are fine. So we have our 0.68, our 0.24, and our 0.08. And then we have to find out, well, how many bacteria is that out of our total, all right? So for our first one, our 0.68, well, we can do 0.68 times 11, and that would give us 7.48 expected, and that would be for our low resistance. So if you think about our 11, we expect 7.48, and we're going to put in the decimals. Then our 0.24 times 11 should give us 2.64 medium resistance bacteria. And then for our high resistance bacteria, we said that was 0.08 of the population. So 0.08 times 11, and that would give us 0.88. And if we add up our 0.88, 2.64, 7.48, we add them up, that should give us back to our 11, which is the same as adding up all of our observed. So that's how you do those calculations. Then you can follow the rest of the steps and get your percent error. Some might be negative, some might be positive, but that will let you know how much the population has changed.